Solve for x1 of t, x2 of t, x3 of t using k1, k2, and k3. Okay, it's giving us all the different values. You may use any tools to solve for x of p of t. Okay. Well, so let's say that we have this system, and on top of these forces, we have another imaginary force that is the strongest that's pulling this way. And if we say that this is, as they said, that this is 0 for x1, this is 0 for x2, and this is 0 for x3, how are we going to model this system? Well, I'm going to model it like this. I'm just going to look, okay, let's color code this. I'm just going to look at this guy. And I'm only going to look at the horizontal forces because the vertical will cancel each other out. We got the normal force here that cancels out with the weight force. So, let's say that I have this little block M1 here. And I have that imaginary force that's the largest one. Well, I have that K1 that's pulling me back, and then I have that K2 that's pulling me forward. Because if this is displaced from equilibrium, this is pulling it to the right, and this spring is trying to bring it back. So I can write for M1, I can model this as M1 times the x sub 1, the double derivative of that, which is going to be the acceleration. So I'm applying the sum of the forces on the block, which is Newton's second law, is going to be minus F1, because F1 is pointing towards the left, so minus, and how can I write this? Well, with Hooke's law is going to be K sub 1 times X sub 1. And then the F2 is going to be also proportional to K2 for the second spring, but it's going to be X sub 2 minus X sub 1 right here. And now let's look at the second one. So let's say I look at this block now, and I'm only going to look at the horizontal forces. So I notice that this block, which is M2, has a force going this way, which is from spring 3, F3, and then we have a force from spring 2 going back, and another forcing function, f of t right here. So how can I model this? Well, if I imagine that this is offset from equilibrium in this direction just a little bit, then m sub 2 is going to be x, the sum of the forces in the x direction on this second block is going to be the two forces pointing towards the left. And what are the two forces? Well, we have the one from F2, which is really pointing back, and it's going to be K2, proportional to K2, x2 minus x1, because it's how much this gets displaced, not considering the fact that this could go in and therefore relax it a little bit. And then we have that minus f of t that's pulling it in. And then we have that force 3, which is pulling it out. I'm going to write that one first. So here I'm going to have a positive, and that's going to be proportional to K3 times what? Well, K3 is going to be x3 minus x2 right here. And then we're going to have that forcing function, which is pushing back, which they said f1 of t is e to the negative 3t. So this is going to be e to the negative 3 times t. And then we can focus on the third block, which is going to be this block over here, Now don't consider that because that wasn't there. And what can we say about it? Well, we can say we have another block, M3, and this block has a force this way, which is a forcing function, and then a force back, which is proportional to F3. So we can model it as M3 x double dot 3. It's the sum of the forces. We got nothing for x1, and we got nothing for x2, but then we have something pulling it back on K3 times x3 minus x2. And notice how this is the same force as this, it's just in the opposite direction because a spring exerts the same force at both ends, just in opposite directions. And then we have plus t squared. So here we have plus t squared right here.